Okay, let's start today's lecture. So far, we have discussed in the combination logic, the designing and the analysis. We have designed half adder, full adder, half subtractor, full subtractor. We then discussed about the parallel adder, how two n-bit numbers are added in the parallel way. We design a full adder. Then we discussed carry look ahead adder, which is a fast adder which overcomes the delay provided in the full adder, and that delay is just only of two gates, and which provides a fast addition of the parallel addition of two n-bit numbers. So here was the look of the carry look ahead adder. It was look like the circuit here. So today we are going to discuss a circuit which is capable of both adding and subtracting two numbers, means which can perform a plus b and a minus b, where a and b are two 4-bit numbers. These bits can be extended up to 8-bit, 16-bit, 64-bit, 32-bit, whatever is the requirement of the hardware. So in this way, in this example, we are going to design an adder subtractor circuit which can add or subtract two numbers a and b, in which both are of 4 bits. So let us discuss the concept behind it, how the addition and subtraction takes place with the same hardware. So here we go. It is desirable to use the same hardware for both operations, that means for the addition and the subtraction. And as we know, if we are performing a minus b, then if we take 2's complement of b and then add it to a, it will perform a minus b. Further, if we have to perform a plus b and the 2's complement of a of b will be same. So for the 2's complement of the positive number is same, but when we take 2's complement of the negative number, it is sign magnitude representation. So let us take a look on the XOR gate, where M and A are two inputs of the XOR gate and F is the output. With the different combinations, with the two inputs, we have four combinations: 0, 0, 0, 1, 1, 0, and 1, 1. And the output is, for the 0, 0, output is 0, 0, 1, output is 1, 1, 0, output is 1, and 1, 1, output is 0. So I can summarize it like when, if I say that M is a controlling input of a logic, if M equals to 0, then F equals to A. When in both cases M equals to 0, F equals to A, 0 to 0, 1 to 1. On the other hand, if I say when M equals to 1, in these two cases, M is equals to 1, and I may say that F equals to A bar. When the A was 0, F is 1. When F is 1, A is 0. Where A is 1, F is 0. So we can summarize that if we have a logic of the XOR gate, if one input is 0, the output of the XOR gate will be other input. If the one input is 1, then the output of the gate will be the complement of the other input. And the same concept we are going to use in the 4-bit adder and subtractor. So here is the circuit. What we have done, we have a 4-bit full adder circuit, which has each full adder have 3 inputs: input carry, A naught, and the B naught. What I have done, I have to perform A minus B. So the B is fed into the full adder using the XOR gate: B0 one XOR gate, B1 one XOR gate, B2 one XOR gate, and B3 of the one XOR gate. Now other input of all XOR gate is equals to M, what we have discussed in the last slide. Here, if M equals to 0, output of the XOR gate is A. If M equals to 1, output of the XOR gate is A bar. So in this manner, we have applied M is the control input, A naught, A1, A2 and A3 are fed directly to the full adder, and B0, B1, B2 and B3 are fed through the XOR gate. Now consider the case when M equals to 0. If M equals to 0, output of the first XOR gate will be B0, here will be B1, here will be B2, here will be B3. So the operation will be just A0 plus B0 plus C0. It will provide some S0 and carry C1. What we have discussed, what we have done in the full adder circuit. Here we can see how it is done in the full adder, in the parallel adder, like this. When M is 0, so it will add A0, B0 and C0 will provide some S0, carry will be forwarded. Then this carry is added to A1, B1, produces some S1, carry is forwarded. This carry is added to A2, B2, S2 is provided, S2 is generated and carry is forwarded. In the same manner, we see here when M equals to 0, input carry is 0, the output of the XOR gate is B0, B1, B2, B3 and the operation is simply addition. Now what happens when we have to subtract A minus B? So in this case, when M equals to 1, the output here will be B0 bar, output will be B1 bar, here will be B2 bar and B3 bar. So what we can say that it is nothing but it is the ones complement of B, and one's complement of B and one is the input carry, then one's complement plus one is the two's complement of the B. So what we are doing here, we are adding A with the two's complement of B, that means it will provide A minus B. That is the purpose behind the circuit. So when M equals to 0, output of the XOR gate will be in the two form. When M equals to 1, output of the XOR gate will be in the complemented form, that is the one's complement of B, and one's complement of B added to the input carry 1, it will provide two's complement and hence we get A minus B. So this is the purpose behind 4-bit adder and subtractor. So here we have used one another XOR gate which is nothing but the overflow. So when we are adding or subtracting two n-bit numbers, it may produce n plus 1 bit output. That is, one is the carry out. The problem if fixed number of bits n are collected for input and output. When we are adding with the paper and pencil, then there is not an issue. Just a moment. So here the overflow is detected with an XOR gate which XORs C3 and C4, because when we are doing the addition or subtraction with the help of paper and pencil, then there is no issue of the space. But when we are adding two numbers in the hardware, then the space is constant. If we are using n bit of register, then it will store only n bit of input or output data, and the carryover or the overflow is a flag in your flip-flop. As the flag is, whenever there is a overflow, the flag V will be set to 1 and it will represent that in the given arithmetic operation, addition or subtraction, there is an overflow, and that will be indicated by the help of a flag. Now let's move to the next topic, that is the BCD addition. As we have done the BCD addition, we represent the numbers in the BCD form. Then we add these numbers just like a simply binary addition. If there is any unused state, means the sum is greater than 9, then what we do, we add extra 6 to the number and represent into the proper BCD form. Because when we are using BCD with the 4-bit input data or 4-bit input number, it will have 16 combination, and but for the BCD we are using only 10 combinations using 0 to 9, and 10 to 15 are unused states. So whenever there is a unused state, we add 6 to that number, and that will convert the output into a proper BCD form. So consider the arithmetic addition of two decimal digits in BCD together with an input carry from a previous stage, that is the maximum possible condition when we are adding two BCD number. Since each input digit does not exceed 9 in case of BCD, the output sum may not be greater than 9 plus 9, that is the two numbers, and 1 is the previous carry. So the maximum output of the sum will be 19. Now here the 1 in the sum being an input carry from the previous addition. Suppose we apply two BCD digits to a 4-bit binary adder. The adder will form the sum in binary and produces a result that ranges from 0 to 19. When we are going to add two BCD numbers A and B, then the sum may be from 0 to 9. 0 will be the case when both inputs A and B are 0 and with the input carry 0, and 19 is the case, that is the maximum when both A and B are 9 and we have an input carry equals to 1. So this would be the output of a BCD adder in the first stage. Now let us derive the truth table for the BCD adder. When we are adding number initially. So from 0 to 9, it is the valid BCD number that will be the carry output. And after that, 0 to 9 here, then 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So these are the output of the first binary adder when we are adding A and B, both are BCD. So here is the decimal representation, 0 to 9, these are the valid decimal inputs, and from 10 to 19, these are the invalid output of the binary adder, which should be avoided. So we can represent these into a valid BCD number. So 0 to 9, it is same. And for 10, we write 1 0, 11 1 1, 1 is 0 0 0 1, like this. So for 9, we write 1 and 9. 1 is represented by the carry and 9 is 1 0 0 1. So this is the way how the output of the BCD is represented by the valid BCD number. So we have to find out a logic, because it is not possible to solve the 5 variable K map. So we have to find out a logic whenever a carry is generated in the sum. We will use the concept of the carry to solve out or to represent the hardware, and we can find out that carry is generated. Just a moment. Now the carry is generated, we can see C is the carry of the sum. So the carry is generated either K is 1, here is the K 1 for the 4 combinations, or we can say or whenever Z8 and Z4 are 1, so Z8 is this or Z4 are 1, or we can say whether Z8 and Z2 are 1. So these are the 4 possible combinations, 3 possible combination whenever there is a carry, then when we have to correct our sum and to represent into the BCD. So the logic for the carry 1, these are the conditions. Carry 1 I have separated out with the lines. The carry is generated either K is 1 or Z8 and Z4 for this combination, and for Z8 and Z2 for these two combinations. Whenever these conditions are satisfied, then the C carry will be 1. So using the same concept, we can design the circuit for the BCD adder as we have C equals to K plus Z4, Z8, Z4 plus Z8, Z2. Now here is the circuit. Here we have number A and number B, 4-bit BCD number. We just add in like just binary number. Input carries 0 and it produces Z1, Z2, Z3 and Z8, and a carry output K. So the carry is 1. Whenever there is a carry, we have to change, or whenever we can say then whenever input is greater than 9, we have to add 6 to the number. So we have used the concept of C. C is 1, either K8 or Z8 Z4 or Z8 Z4 or Z8 and Z2. Whenever these conditions are satisfied, the output carry will be 1. So we have used the same number will be added to 6, and 6 is produced 0, 1 1 0. Whenever there is a carry, it will add 0 1 1 0, that is 6 to the number. Whenever there is no carry, it will add 0 0 0 0. So it will add 0, and now here, from here you can find out the exact BCD number which is to be stored in the register. So this is the concept of BCD addition. Whenever the binary sum is greater than 9, we have to add 6, and 6 is added with the help of this carry generation. Whenever carry is 1, 6 is added. Whenever there is no carry, then 0 will be added. The number will be valid BCD number. So now let's move to the next. That question has been asked in your examination 4 to 5 times. BCD to 7 segment decoder. That is a very much important, and in the daily use you have seen this BCD to 7 segment decoder many times. That is display of your computer, laptop, or the display of your calculator, display on the red light, display on your lift system. These are the BCD to 7 segment decoders. So the specifications are digital readouts on many digital products often uses LED 7 segment display. It looks like this. So it has 7 segments: A, B, C, D, E, F, and G. These are the 7 segments. That's why we say BCD to 7 segment decoder. So the input will always be a BCD number 0 to 9, and display will be of 7 segment. Each digit is created by lighting the appropriate segment, and the segment are labeled as A, B, C, D, E, F, G. Lighting means whichever segment is one, that will glow. Otherwise, it will be black. The decoder takes a BCD input and outputs the correct code for the 7 segment display. Here, the input is 4-bit valid BCD coded input. Output is 7 bits through A through G for each of the segment of the display. And the operations is it decodes the input to activate the current segment. So we have to design a hardware that will take BCD as input and will provide the proper output that will glow the proper segment A through G, and which will display your normal decimal number 0 to 9. You have seen many times in the lift, in the at the red light, the display in the counter, that is done with the help of BCD to 7 segment decoder or BCD to 7 segment display. Now let us construct the truth table for the BCD 7 segment decoder. Here is your display. Input is a 4-bit BCD, means 0 to 9. We have BCD 0000, 0001 up to 1001, that is 9. And the output, suppose we have to glow or we have to show 0. So A, B, C, D, E, F, these should be 1 and rest should be 0. So G will be will not display, and we'll see A, B, C, D, E, F. Suppose we have to display 1, then B and C should be 1. So B and C should be 1. Suppose we have to display 2. So 2 should be A, B, G, E, D. In the 2, A, B, D, F, D, E, G. Suppose we have to display 3. So 3 will be A, B, C, D, and G. Suppose we have to display 9. So 9 will be G, F, A, B, C. Like this. So in this way, we can design a BCD to 7 segment decoder, and the rest of the combinations will be 0. So we need not to put any don't care condition. We simply put, because we have to disable whichever bit is not required. So when we are going to use BCD to 7 segment decoder, the input will be 0 to 9 in the BCD, and the output will be as per the requirements to glue the particular segment. So the process is we have to solve 1, 2, 3, 4, 5, 6, 7 K-maps from A to G, and the output of the 7 segment will be like this: A, B, C, D, E, F, G. There will be the output, and to implement it, it requires 27 AND gates and 7 OR gates. With the help of this, we can implement our circuit. The implementation of the circuit is your for home assignment. Then you all will try to solve with the help of the K-map, and keep in mind that the rest of the states will not be don't care. It will be treated as zero. Okay, the next topic is the magnitude decoder or magnitude comparator. It is basically magnitude comparator, which compares two binary numbers A and B. Suppose we have two numbers A and B. A is A0, A1, A2 and A3. B is B0, B1, B2 and B3. We have to compare their magnitude, and we'll provide an output. And there will be three outputs: either A equals to B, sorry, A greater than B, or A less than B. So in the magnitude comparator, we have two numbers. Numbers will be n bit. We have three outputs: A equals to B, A greater than B, and A is less than B. So when we look into the block diagram, we see that there is 8 bit of output, 4 bit A, 4 bit B, and it is not possible to design a comparator with a conventional scheme that first we draw the truth table, then we solve the 2 to the power 8, that is 128 combinations of the input, then we solve the K-map. So we have to again look for a unorthodox technique or logic. We have to find out the logic that how can we design a comparator without solving a K-map, because it is very much hectic to solve an 8-bit input K-map either with the help of K-map, or we have to minimize with the help of Boolean algebra. So we have to find out a logic, and here we are going to find out a logic for the same. For the classical approach, 3 output, 2 n inputs, large logic complexity when n is greater than 3. We have to find out an alternative approach, and that is a two-step process which we are going to discuss here, how to design a magnitude comparator. Now suppose define xi is a combination logic is equals to ai XNOR b. XNOR says ai bi plus ai bar bi bar. This is our logic. So we have used an XOR gate, and the output of the XOR gate, we have defined it xi sorry, and xi is equals to ai bi plus ai bar bi bar. That is your XNOR gate. Now suppose I have to find out, let's look into this. The output xi will be 1 if a equals to b. That means if both are 0, then 0 0 0, and 0 bar 0 bar, that is 1 equals to 1. If both are different, then the output will be 0. So we can define the logic of XNOR gate. If both inputs are equal, then the output will be 1. Either they are 0 or they are 1. If both inputs are different, then the output will be 0. So that is the logic we are going to discuss here. Now let us define A equals to B. A will be equals to B if x3, that means B3 is equals to A3, and x2, that is B2 is equals to A2, and x1, that is A1 is equals to B1, and x0, that is A0 equals to B0. If all 4 conditions are satisfied, then A equals to B. That will be the first output. X3 defines that A3 equals to B3. Now suppose we have to find out the logic if f for f2, and f2 is defined as A is greater than B. So whenever A will be greater than B, either A3 is greater than B3, और अगर ऐसा नहीं है then A3 is equals to B3, या तो दोनों either both are 0 or both are 1. If this condition is true, then A3 is equals to B3 and A2 should be greater than B2. If this condition is not satisfied, that means both A3 is equals to B3 and A2 equals to B2. This condition is here, A3 equals to B3 and A2 equals to B2. Then we have to look into A1. Now A1 should be greater than B1. Then A will be greater than B. If this condition is also not satisfied, that means A3 equals to B3 and A2 equals to B2 and A1 equals to B1. Now the condition is that A naught should be greater than B naught. If this condition is also not satisfied, then A equals to B. So we have to find out the logic behind it. If A3 is greater than B3, that means A3 should be 1 and B3 should be 0. So we can write the logic A3 B3 bar. So here is A3 B3 bar. If this condition is not satisfied, that means A3 equals to B3, that means X3, and A2 B2 bar means A2 is 1, B2 is 0. If this condition is not satisfied, that means X3 and X2, that means X3 and X2 means A3 is equals to B3 and A2 equals to B2, and in that condition we should have A1 should be 1 and B1 should be 0. So A1 B1 bar, or X3 X2 X1 all bits are equal and A naught is greater than B naught. So this is the logic behind the output function F2, for which we are obtaining A is greater than B. In the same manner, we can find out the logic for A is less than B, and in that case, if B is greater than A, then A3 should be 0, B3 should be 1, so A3 bar B3, or if A3 equals to B3, then X3, or A2 should be 0, A2 bar, and B2 should be 1, or X3 X2, that means both A3 and B3, A2 and B2 are equal, then A1 should be A1 should be 0, so A1 bar B1, or A3 sorry X3 X2 X1, all three bits are 0, then A0 is 0 and B1 is 1, so A0 bar and B0. So this is the logic behind a magnitude comparator, and this I should be of n bit. If you are using a 64-bit processor, then I will range from 0 to 63. Here we have used 4-bit, so we have used I equals to 0 to 3. So here is your implementation of the logic, what we have discussed in the previous slide. We have A3 and B3. So A3 bar, B3, A3, B3 bar, or then we have put it NOT gate, that is X3. So we have generated X3, X2, X1, X0. When we AND both of four junction, when we AND both of these outputs, then it is A equals to B. We have relation for A greater than B and A less than B. In this way, we can find our design a magnitude comparator